in Chapter 7 we were introduced to a variety of things, but mainly using normal distributions to come up with probabilities, and in particular we were looking at the distribution of a sample mean. And so we really have two cases in terms of a sample and in terms of what we could know about a population. So in Chapter 7 we were exploring the idea of having a known population variance, okay, and when you know the population variance, that's having this kind of supreme being like knowledge that allows us to make a lot of assumptions, namely that we know the distribution is normal. So if I knew that a value x, some variable x, was distributed normally with a mean of mu and a standard deviation sigma, okay, and then I were to draw a sample of size n from this population, the distribution of all such sample means, so in other words, if you had every possible sample of size n and looked at every possible sample mean coming from those samples, the distribution of the sample mean would be as follows. So x bar pulled from a sample of size n would also be distributed normally. It would have a mean of mu and a standard deviation of sigma divided by the square root of n. Okay, this bit right here, we call this the standard error. Okay, and I'll talk a little bit about that in a moment. It stands in for the standard deviation of the sample of the sample means. And so what that tells us, then, we can compute a z-score for a sample mean. So a z-score, z is always equal to the observation minus the mean value divided by whatever you have for the standard deviation. Alright, so for us, if we had, let's look at an example. If we had a population, here's our example, has a mean of 14 and standard deviation of 1, okay, if we know that x is distributed, it's my squiggle line's not coming out very well, distributed normally, and so in other words mean of 14, standard deviation of 1, suppose we draw a random sample of size 25, and I picked 25 just to be easy. Square root of 25 is nice. So let's suppose we randomly choose a sample of size 25 from this normally distributed population. Okay, what would be the probability of observing a sample mean of something greater than 14.4? Okay, so find the probability of observing a sample mean of 14.4. In other words, if we were to draw a sample of size 25, how likely is it that we would see a center observation be 14.4 if the normal mean is 14? Okay, so the way we would figure this out, we would say, okay, well, this, to translate, what's the probability of x bar being greater than or equal to 14.4? Well, this is the same thing as the probability of z being greater than or equal to whatever the z-score of this observation is. And so we know that the 14.4 minus the mean, and then we can divide it by its standard deviation, which in this case utilizes the standard error. So this part right here is the mean from the distribution of x bar. This 1 over root 25 is the standard error, the standard deviation for x bar. Okay, we call it standard error to separate it from just a traditional standard deviation, and again in just a moment I'll kind of give a broader picture of why it's called a standard error. Okay, so really we're looking at the probability of z being greater than or equal to 0.4 divided by 0.2, so that's just the value 2. So how likely would it be that we drew a sample of 25 and the sample mean was greater than or equal to 14.4? Well, that's going to be the same likelihood as observing a z-score of something greater than 2. Okay. Now, if we drew a picture of this, let me skip ahead. If we drew a picture of this, here's our normal curve. And I'll see how well this goes. So close. And we've centered this down now at 14. The standard deviation is 14.2, and down here it's negative, not negative, it's 13.8. That defines the middle 68%. Okay, so what's the likelihood of observing a value that's all the way up here at 14.4? So in other words, how likely is it to have a sample mean that comes out of this region? Okay, well, the probability, we can convert this to a z graph. Let's see how well I can do that a second time. Not very well. So here's 0, and we computed a z-score for the 14.4. We computed a z-score of 2, and so we're trying to say what's the probability of landing above 2. So we can look it up in the table and notice I couldn't find an electronic version of the table that matched the one in our book. But if you look it up in the table to find the tail probability, you would see that the probability of z being greater than or equal to 2 is equal to 0.0228. So in other words, the probability of having a sample mean drawn from a sample of size 25 exceed 14.4 is the same as the probability here, so that's going to be 2.28%. So that's not very likely. Okay, so the probability of observing that value or something more extreme is only 2.28%. Okay, I want to now explain a little bit more about the central limit theorem and kind of help us understand why the distribution of x bar is the way it is. Okay, so if we were to look at a value x and it's distributed normally with a mean mu and a standard deviation sigma, we draw a sample of size n. Sample size n. Okay, then we know from the central limit theorem, and I'm just going to say central limit theorem tells us tells us that x bar is distributed normally with a mean mu and a standard deviation sigma divided by square root of n. Okay, now I'm not going to go into any great detail about the math derivation of this expression, but I just want to give you some kind of intuitive sense about it. I might have drawn this picture before, I can't remember, but let's list out our full population. Let's just draw a box here that represents the full population. Okay, there we go. So this box is the full population, and the center of the box, let's say it's right here. Let me put a cross in here. Okay, that's the center. That's where mu is at. Okay, now I'm going to draw a smaller shape, and the shape is, let's just say, a circle, and the size of the circle is going to be dictated by the sample size. Okay, so okay, here's in this color. If I were to consistently draw samples of size n, that is small, and the center there, that's your x bar. That's your x bar. Okay, that's very far away from our mu, and I draw a different sample. Maybe it's right here. Okay, it's the same size, and that's a new x bar, and it's a little bit closer, but it's still kind of far away. Maybe we're really good and we get a sample, but our center of the sample is all the way over here, and so that's not exactly mean, but the mean, but it's pretty darn close. Now, as we increase the size of the sample, we're going to increase the size of the circle. I'll switch to a different color, and now let's say that I increased it twofold, and so I'm going to try to draw a circle that's twice as big. It's more than, but that's okay. So now here's our center, and here's x bar, and I draw a new sample over here, and here's our center, here's X bar. We're a little bit closer, but notice that the red circles take up more space. So if I could, I would animate this and let the circles kind of wiggle around. Maybe I could do that. Okay, kind of, yeah. So think of this circle. If I kind of, it doesn't have as many places to go in the box. So if I increase the size of the sample, it doesn't have as much wiggle room. Okay, so we see that we increase the size of the sample and make it really small. There's lots of places for this thing to bounce around. If we just increase it, though, it kind of doesn't move around as much. And so that's the idea right here. The premise is to say that the center, which is now all sorts of moved, the center should be the distance from the X bar center and the true mean center should be dependent on the size of the sample. So if I take more of the population into consideration, I should be much closer to the true mean. And that closeness we're going to define as the standard error, but basing it on the standard deviation.